Hello everyone. So the title of my project is Transient Stability Analysis and Integration of Renewable Energy in Power Grids using ETAP software. So the background or objective of my project is by using ETAP software, we can build and optimize a microgrid system that uses a high proportion of renewable energy sources. So first of all, we will design a conventional power system. So that will consist of two diesel generators. Afterward, renewable sources will be gradually integrated into the system to observe the overall behavior of the system. Then we will conduct some contingency analysis of the overall system, such as by doing line trips, short circuits, or unexpected loss of a major power source that will allow us to observe the real life scenario of this proposed scheme. And eventually that will allow us to create a stable, reliable, and resilient power system that can handle load needs, account for renewable energy sources, irregular output as well. So there are some problem statements. That's why we are doing this project. So first of all, the variable nature of the renewable sources have posed certain difficulties in the power system, such as irregular voltage regulation, frequency regulation, high short circuit current, etc., and which eventually leads some power quality issues and eventually triggering the protection relays that could result a complete blackout of the overall power system. And due to the fluctuating output of the wind and PV sources, there is always some mismatch between supply and demand between the prosumers and consumers. And when we will integrate the renewable source into the system, that needs some significant upgradation of the existing infrastructure, because by establishing a renewable system we need to conduct a high upfront cost, which needs some additional cost in the construction period. And last of all, sophisticated and expensive power management technologies like smart grids and AI-based forecasting systems are required for the optimal integration of the renewable energy sources as well. So considering these problem statements, we need to do a complete analysis in a power station software to make sure the overall system will behave accordingly as per the industry standards. So the prospective solutions of the above problems are: we can design a microgrid system as a uh, uh, right now microgrid have become effective alternative to these solutions, to these problems. And also by designing a hybrid microgrid, that means more than one power sources, we can eliminate risk of low output from one sources, as there is always some alternative from other sources. And microgrid can function with and without primary grid and manage multiple renewables, which increasing the resilience and reliability of the system. And last of all, a power system software addresses these difficulties of integrating renewable energy in a power system that maximizes sustainable renewable energy usage while maintaining stability and reliability. So before implementing a real application, if we can analyze the overall system in a power system software, that will give us some accurate data of the system, which will help us to design the system more accurately and precisely in the real life application. So the proposed project methodology are: the project aims to use ETAP software to build and optimize a microgrid system that will use wind and PV sources in our case. So the proposed methodology includes as following. First of all, we will design a microgrid system. Then after we design the microgrid system in ETAP software, then we do the load flow analysis. So after doing the load flow analysis, then we will gradually integrate wind and PV resources here. So after the integration of the PV and wind resources, then we'll do some transient stability analysis. So which will include by conducting some fault into the system, by doing the short circuit fault into the system, or by isolating one of the feeders from the system to check whether the system can maintain stability after the fault or not. After everything is done, then we'll optimize and validate the whole power system in ETAP software. So this is just a flowchart of the project methodology. So we will start from design of the microgrid system. Then we will do the load flow and fault analysis. So if the load and fault analysis are within the system stability, then we will gradually integrate the solar and wind into the microgrid. Then after that, we again will conduct a load flow analysis in the system. And after that load flow analysis done, this overall system dynamic stability analysis will be done. So if these two things are within the stability limit, then we can say the microgrid design is completed. So we have designed a single line diagram of the proposed microgrid in ETS software. So we can see that there are two generators here, each rated 4 megawatt. And for the load consumption purposes, we have two auxiliary loads here, each rated 1.5 MVA, and we have a 1875 kilowatt big motor in here. And for the renewable sources, we have used wind turbine and PV sources in here. The capacity of the wind turbine was 2 megawatt, and the capacity of the PV was 2000 kilowatt in here. Overall system is connected to a busbar system, and the busbar is connected to a 10 MVA power transformer that eventually connected to the infinite power grid. So this is just a simple microgrid that has been designed in the ETAP software. So after that, we do the load flow analysis in the system. So these red lines indicates the power flow from different sources in here. So as we can see that depending upon the consumption, only generator 2 is now in live condition in here, and it dispatches 250.2 ampere in here. And we haven't conducted the load flow analysis on the renewable energy sources yet from this scheme yet. And the auxiliary 1 and auxiliary 2 load have consumed loads from the generators in here, and also the big motor is consuming 112 ampere current from the generator 2. So after that, we have integrated a fault analysis in the main busbar. So when we actually integrate a short circuit fault in the main busbar, that's how the overall system behaves. So what we can see that when there is no renewable sources, this is the graph of the short circuit current, and with the renewable sources, this is the graph of the short circuit current. As we can see that there is no noticeable difference between the short circuit graph with and without the renewable sources. So we can conclude that even with the integration of the renewable energy sources, there is no noticeable difference in the short circuit current, so that we don't have to upgrade the existing breakers in the system. So without any renewable, the short circuit value is 46.934 kiloampere, and after the introduction of the PV and wind resources, the short circuit current is 47.217 kiloampere, which is the not too higher from the original value. So we don't have to upgrade the existing breakers. I think every existing breakers have a capacity of until like 60 or 80 kiloampere short circuit value, so that the existing breaker will serve the purpose here. So now we will do the transient stability analysis after the integration of the renewable sources. So for the transient stability analysis, we will take a 20-second time span in here. We will consider all the sources into the system here. And for this transient stability analysis, we will integrate a line to ground fault in the system, which will activate in 1 second. And the duration of the fault will be zero point 0.5 seconds. So the fault will be last until 1.5 seconds. That means the duration of the fault is 0.5 seconds. So after the fault is cleared in 1.5 seconds, then we will analyze various parameters of generators, busbars to check whether they recover from the disturbance or not. And it is natural that the sooner the system stabilizes, the more robust is the system. So this is the transient stability report of the generator parameters in here. So the left side, the transient stability report with all sources, and the right side is without PV and wind sources. So if we carefully notice the two graphs, we can see that there is no noticeable difference in the generator power angle, generator speed and megawatt after the fault is cleared. So fault is cleared is 1.5 seconds. So after the fault is cleared, we can see that approximately after 5 seconds, the generator power angle, speed and megawatt stabilizes. Same for without wind and PV cases as well. So after the fault is clear is 1.5 second, approximately after 5 second, the power angle, speed and megawatt of the generator stabilizes. So the both scenario actually tells us the same cases, which is there is no huge disturbance that has been caused by the PV and wind resources in the existing power grid. Now we can see the busbar parameters with and without PV and wind turbine. So just like the previous slides, we can see that there is no noticeable difference between these two ones. So we can safely assume that even after the integration of the PV and wind resources, the existing system parameter doesn't change drastically. Now, one of the most important aspects of this project is the role of wind turbine inertia. So the wind turbine inertia plays a vital role in system stability. So for this paper, we will analyze the transient stability of the wind turbine under different inertia value in line to ground fault. We will observe that the high inertia wind turbine will maintain better stability after the fault clearance than low inertia wind turbine. And this analysis will provide an important aspect to the decision makers while they integrate renewable energy sources into the existing power system. So the bigger the inertia constant of the wind turbine, the sooner the wind turbine becomes stabilized, because the bigger the system is, it takes more time to become destabilized. For example, if there is any voltage or frequency disturbance in the system, the bigger the power sources is, it takes more time to get destabilized from the existing system. But the smaller system, for example, like small wind turbine, will get destabilized or will take time to become more stabilized after the fault clearance, because the inertia constant is less in this case. So this picture will provide us a clear picture of the above description. So the right hand side picture tells us when the wind turbine inertia is zero point 0.3, and the left hand side picture tells us that when the inertia constant is 0.06. So we can clearly see that when the inertia constant is 0.06, even after the fault is cleared after 1.5 seconds, the wind turbine takes like forever to get stabilized. For example, we can see that the load, current, and the speed of the wind turbine takes like more than 10 seconds to get stabilized. But when the inertia of the wind turbine is zero point 0.3, even after the fault is cleared in 1.5 seconds, approximately after like 5 seconds, the speed, current, and the megawatt value of the wind turbine stabilizes. So by comparing these two pictures, we can say that the higher the inertia constant, the sooner the wind turbine will get stabilized. But the lower inertia constant wind turbine will take more time to get stabilized after the fault clearance. So these are some key points of my project. So the integration of the renewable sources does not create any major disturbance, and except the inertia thing. So in our case, for the transient stability analysis, we introduce a line to ground fault, that is IEC 61363 fault in the system to analyze the parameters. Short circuit current of the main busbar does not increase by a huge margin after the addition of the PV and wind turbine. And as discussed above, the wind turbine inertia plays a pivotal role in the system stability in here. The high inertia wind turbine regain the normal condition quicker than the low inertia wind turbine. Therefore, the decision maker should fix a minimum inertia value of wind turbine during the interconnection process. So when they will integrate any new wind turbine into the system, they should check the inertia constant of the wind turbines. They should check the manufacturer nameplate rating to another system parameters. Because if the inertia constant is too low, and that will create some major disturbance after the even after the fault is cleared from the system. So in the end, we can say that this study provides a clear illustration of the challenges involved in integrating a significant percentage of renewable energy sources into the power grid. We investigated the gradual integration of solar and wind power resources into the main grid, and we examined their effect and design by modeling in ETAP software. This study also shows that by integrating renewable energy into the primary electrical system is feasible and reliable. The findings drawn from the simulated data lay a strong foundation for implementing such strategies in practical applications, which will allow us to move one step closer to a future of sustainable energy.